Woohoo, students! All right, today we're going to talk some more about reactivity. We talked a little bit about it last Thursday with your periodic table. We drew one reactivity arrow on there, but we're going to go a little bit deeper today. So the first thing I want you to do is, we drew some arrows on your last periodic table for reactivity. I want you to draw some arrows on this periodic table for reactivity. So this time we're going to first draw an arrow going from 1 to 4, and then it's going to stop at 4. See how it stops at 4, pointing to the right. And then I want you to draw another arrow meeting up with this one, but we're going to start it over group 7. Not over group 8, over group 7. So just like this. And they're going to meet in the middle. We're going to label both of these arrows as decreasing. Because what happens with reactivity is group 1 and group 7 are the most reactive groups, and as you move inwards on the periodic table, the reactivity is going to decrease. So it goes from high reactivity with 1 and 7 to low reactivity with group 4. So let's review a little bit. Does anyone remember the name of the group 1A metals? Anyone? Anyone? Correct. They are the alkali metals. So down here on the bottom, go ahead and let's label that again. These are the alkali metals. And we're going to switch to group 8A. Does anyone remember what group 8 is called? Anyone? Anyone? Very good. They're the noble gases. You guys are so smart. You must have wonderful science teachers. Okay. We're going to add another group on here that we haven't talked about yet. We're going to go with group 7. Group 7A is called the halogens. Halogens. Okay, so we've got the alkali metals, the halogens, and the noble gases. Groups 1, 7, and 8. While we're looking at the group numbers, let's go ahead and circle. We're going to circle all the group numbers except for 8. I'm going to tell you why in just a minute. And make sure you're circling the A numbers too, not the teen numbers, 14, 15, 16. We just want to circle the A numbers because they help us remember. What do they help us remember? What's the same as group numbers? Does anyone know? Can anyone remember? Valence electrons. The group numbers are the same as the number of valence electrons. So all of the elements in group 1 have 1 valence electron. All of the elements in group 2 have 2 valence electrons, and so on. So when we talk about valence electrons, that's where reactivity comes from, when elements are going to get rid of and gain valence electrons. So for instance, the alkali metals are readily, very easily going to give up this 1 valence electron to another atom that needs 1. And that's going to be the halogens in group 7. And the reason the halogens want just 1 more is because all atoms on the periodic table want to have their last energy level be full of electrons with 8 valence electrons. And that's called the magic 8 rule. We're actually going to write that on our periodic table down here. I want you to write atoms want the magic 8. We're going to put a bubble around it because it's important. Atoms always want the magic 8. They're always looking for other atoms to either give them an electron or to give up electrons to other atoms so they can get the magic 8 valence electrons. That's why noble gases don't bond with any other elements. They are noble, they're stuck up, they don't need anybody else, they're not reactive at all because they already have 8 valence electrons. They're in group 8A. So go ahead and circle group 8A like I did there. Draw an arrow, and I want you to write, they already have the magic 8. That's why they don't react at all. And we're going to write that in the group. So kind of turn it to the side here. We're going to write, actually we're going to write it going down. Not reactive. The noble gases are not reactive at all. They don't react with any other atom, ever. They won't do it. They never, ever will. Okay, so on the alkali metals and the halogens, so we can kind of just not even worry about the noble gases, not even worry about group 8A when we talk about reactivity. We're just looking at 1 through 7. So starting with the alkali metals and the halogens, these are the most reactive groups because the halogens have 7 electrons. They're really, really close to the magic 8. And alkali metals only have 1 extra. They're really, really close to the magic 8. They just want to get rid of their 1, and the halogens just need to find 1 more. So they're super, super reactive. Whereas when you move in, they need to get rid of more or find more so they get less reactive. So for instance, the elements in group 6, they have 6 valence electrons, so they have to find 2 valence electrons. That's a little bit harder, so they're not as reactive. Whereas in group 2A, they have 2 to get rid of. That's a lot to get rid of, so they're not as reactive. And as you go in, it gets less and less reactive. So 1 and 7 are the most reactive. Let's write that on here as well. So across group 1A, write most reactive, and also across group 7A, write most reactive. Okay? So alkali metals, halogens, most reactive. As you move in, they become less reactive until you get to group 4A. That's the least reactive group because they either need to find 4 or gain 4, and that's a lot. That's a lot of work for them to do, so it's not very reactive. Okay, so I want to look at kind of a visualization that can help you understand a little bit better how the electrons move from one atom to another. So I'm going to draw 2 atoms here. I'm going to do sodium and chlorine. Does anyone know what it's called when you put sodium and chlorine together? It's the formula for table salt, sodium chloride. So sodium is in group 1, period 3, and chlorine is in group 7, also period 3. So when I go to draw my Bohr models, I'm going to do my nucleus first, my protons and neutrons. It's where all of the mass of the atom comes from. Sodium has 11 protons and 12 neutrons for a mass of 23. Chlorine has 17 protons and 18 neutrons. Okay, you should remember from APE that the number of protons is equal to the number of electrons. So sodium has 11 protons, so it has 11 electrons. Before I can add the electrons, though, I need to draw my energy levels. I don't know how many energy levels to draw. Which one of these, the group number or the period number, would tell me how many energy levels to draw? That would be the period number would tell me how many. So it's in period 3, so it has 3 energy levels. 1, 2, 3. And chlorine is also in period 3. So 1, 2, 3. Move my camera down just a little there. Okay, now you can see that better. So now all I have left is to put my electrons on. And instead of drawing my electrons this time, I'm going to use some little dots to kind of help us see how they move. So remember, when you put your electrons on your Bohr model, you have to follow the 2-8-8 rule. Only 2 electrons can go in the first level, and 8 can go in the second level. Don't want to drop any here. 1, 2, 3, 4, 5, 6, 7, 8. So I've got 2 here, 8 in the second level. 2 plus 8 is 10, and 1 more. Here's my 1 valence electron. Group 1, 1 valence electron. So I've double checked my work, it's correct. Chlorine has 17 protons, so it has 17 electrons. Put those guys on there. Got to follow the 2-8-8 rule again. So 2 here, and then I can put 8 on the next one. Oh my goodness, there's so many electrons. Let me move those over here. 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2. So I've got 2 in my first level, 8 in my second level, and now I need 7 more little rascals. They're hard to move around. 1, 2, 3, 4, 5, 6, 7. Okay, so I know that I've done my Bohr model for chlorine right because it's in group 7. That means it has 7 valence electrons. So 1, 2, 3, 4, 5, 6, 7, 7 valence electrons. And it's in group 1 for sodium, 1 valence electron. So what happens when two elements react together, when we're talking about reactivity, when two elements react, what happens is they are sharing valence electrons. They're either kicking them off or they're taking them in. And when that movement of the valence electrons happens, that's the energy you see in an explosion or a spark or smoke or bubbles, any kind of chemical change you see when two elements react. The energy you see comes from these electrons moving. Uh-oh. Don't get crazy. Stay on there. So I'm going to show you just exactly what happens. So sodium has this 1 valence electron out here. What happened? I lost some guys moved here. Okay, so it has my 1 valence electron. Sodium really wants to have the magic 8. Wants to have that magic 8 rule. So if all it has to do is get rid of this 1, and then it can have 8 valence electrons in its second energy level. And chlorine has 7. All it needs is 1 more. So they find each other, and sodium says, here, buddy, pew, kick it off, and you can have that one. Now I have 8, you have 8, we're both happy. So they've reacted together. So then you would see some kind of physical change occur, some kind of reaction. So when this 1 electron moves over here, that's 2 elements reacting. So group 1 and group 7, group 1 most reactive, group 7 most reactive. That happens very readily. Those two are going to react together because just needs 1 more, just needs to get rid of 1. That's not very much work, so they're super reactive. Okay, so let me just show you that one more time. Okay, so just remember, when reactivity occurs, an element wants to shake off, oh my gosh, there's the cat. Sorry about that. Wants to shake off its valence electron. Ready? Shake, 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 shake. Shake it off, shake it off. Ta-da! So sodium shakes off its valence electron to chlorine, and they react together, and that is all. Have a lovely day.